Thanks guys, thanks for coming out. Welcome back. Dr. Harrod, and we're doing chapter 13 in the Heizer Render textbook. Today's topic is aggregate planning. And what aggregate planning is it's the top level planning of a manufacturing firm or a business firm's operations. We're really talking about scheduling here in tonight's discussion. We've started out the semester talking about kind of strategic planning things, including forecasting and project planning, and then we went into quality control and kind of numerical things like inventory planning. We looked at inventory planning, but this second half of the semester, this last third, maybe last third of the semester, we're really going to focus on scheduling. And these next few chapters, 13, 14, 15, are all about scheduling. We're looking at various types of scheduling within the manufacturing, within the operations of the firm. So today, we're going to start out at the strategic level, or the long-term planning level of the firm. We're looking at aggregate planning. What does that mean, aggregate? It means we're just looking at gross volumes. We're not looking at the details. We're not paying attention to specific constraints about whether we can actually get those products made due to the inventory of parts, or whether there are any issues with transportation or employee labor force or anything. We're going to aggregate that all out, relax a lot of constraints, and just look at the total volumes that we do, and look at our operations and our planning from a very top level, kind of zooming out on the map. We're zooming the camera out of the map and really looking at things at a very broad level. We're typically looking at things at the monthly or quarterly level. So we're not looking at any particular level of detail. We're looking at gross volumes. So today we're talking about strategic and long-term planning. This is aggregate planning right there. In the next chapter, here in chapter 14, we'll look at a tactical type of planning. We'll start looking at things when we're actually constrained by what we have in inventory, or by what we have as a demand from the customer, or by the combinations of pieces and parts we have to put together. And we will look at that in chapter 14. And then finally, about 3 weeks from now in chapter 15, we'll look at a really detailed day-by-day plan in terms of what employee does what job, and what is going to get done, and which pieces and parts do we make first. The problem, and the reason we separate this all out, is really, well, twofold. We separate this out in these stages for a couple of different reasons. Number one, it would be very mathematically difficult to do all of this in one big mathematical problem. The problem would become so complicated and so dense for a large firm that we really couldn't come to a very good solution. We would have an enormously difficult time formulating a mathematical program that did all of these layers of planning all together. But secondly, we also separate these things out to kind of create buffers between decisions, between planning environments. That is, if we attempted to do all of this all together, we might end up with something called nervousness. That is, where small changes here at the really tactical daily plan, if we keep transmitting that information back up the chain to the upper levels, and keep changing those upper level plans every time something small changes day to day, it creates this constant jittery change, this constant daily restructuring, and it's called nervousness. And that's actually something we have to avoid. And in some firms and operating plans, they actually have formal rules. They will say, we're going to calm our plan down by actually enforcing some constraints, by actually saying, okay, we've made this plan, we're going to freeze that plan, and we're going to stick with it. And we're not going to change it unless there's just a complete emergency, unless there's just an enormously difficult problem, or a weather issue, or just an enormous economic disruption or something. Other than that, very often these strategic plans are locked in. They're frozen in to avoid too much disruption and too much replanning at the firm level. So we're going to look at aggregate planning today. We're looking at these quarterly and long-term strategies. And so we're really having to consider, where are we going to get our stuff? How are we going to make our stuff? How much quantity are we going to make? And where are we going to source that stuff? And so let's talk for a minute about where we might source things. If we're a manufacturer, where are we going to get things from? And typically, in nearly most firms, most types of manufacturing firms, we have some choices in where we source things. We can source things, we can actually source them from inside. We can make them. So we can produce those things. We can source them outside. We can outsource them. We can subcontract them. And then within those two flavors, we have a lot of subdivisions. We could, for example, internally, we can produce these during regular production, or we can produce these things during overtime, or some kind of extra scheduled production, some kind of extra additional effort. Usually overtime is the standard definition. Overtime being you pay someone to work extra hours. You pay them to work beyond the normal workday. You pay them to come in on a holiday or on a Saturday or on a Sunday. And typically that's more expensive. Typically it's more expensive. We have to pay those people extra money to compensate them for their inconvenience, for them having to come in on a day that would normally be a holiday or a day they have to get away from their family. So typically the overtime is more expensive. Sometimes we can also use inventory as a buffer. So we have inventory as a source, an internal source of product, and that inventory is coming from other time periods. We produced in other time periods, and we have that inventory to even out our production cycles and even out our demand. So we have this, and then we have these different ways of sourcing things, and then we have our demand. And I think I'll put it right about here. Make some space on the board here. And then we have demand. We have demand, and that demand is experienced by direct customer orders, or it's sometimes dimensioned by a forecast. Sometimes some firms are only going to make things in response to direct customer orders. Those are typically called make-to-order firms. And other firms that make to forecast and then are putting inventory and selling as the customer comes up to the store. Those are make to stock. And so an automobile manufacturer is make to stock. Automobile manufacturer makes cars. They put them on the dealer lot, and then the people come buy them, but they make the cars first before they know exactly when the customers want those cars. Whereas other firms are made to order. Certainly if you go online and you buy monogrammed clothing, if you buy your initials sewn into a shirt, that would be made to order, because they would not make that shirt until you would place the order and told them you want them to make that shirt for you with your initials. But we have a demand, and very often we do have some fluctuations in demand, either because of seasonal changes or because of just a natural supply fluctuations from the customer. So we will either have a forecast of that demand, or if it's a make-to-order company, we will have firm orders. We will actually have firm planned demand that we're trying to respond to. But we'll have this demand, and if we have, let's say we're marking this chart in months here. These are all months right here. We have demand, and then maybe it's something else, and then it goes up again, and then it goes down, and then it goes up again, and then it goes demand down, and it goes up again, and it goes down, and it goes up. We have these different patterns of demand. We have to figure out how we're going to respond to that demand. Now, typically, we have a couple of ways besides these different sources. We have some additional possible ways to respond to this. We could, in fact, manipulate our regular production. We could actually make changes to our facility, either by changing the number of people that we employ or changing the capabilities of our facility to make product. And typically that decision is referred to as hire fire. Now, I will not, in this lecture, I will not spend any time discussing hire fire. It doesn't fit neatly into the methods we're going to learn tonight. Generally speaking, if you do hire fire, there is a dollar cost for hiring new employees and training them and setting up a workspace for them. And then very often in many climates and many political cultures, there is a dollar cost for firing employees, for closing down production. There's a cost of compensation for employees when they're fired, and there's the transition cost. There's frequently a regulatory burden or unemployment insurance or these kinds of things. So either way, there's a dollar cost when you make changes in your production capability. So when we look at this consumer demand here that's going up and down, one response could be to hire and fire. That is, to hire more employees when demand is high, and then to lay them off, and then hire employees and lay them off, and hire employees and lay them off. And the cost structure and the strategic plan for that hire-fire decision is typically a very manual, labor-intensive scheduling decision. You have to actually work out the possibilities manually and check what they would cost and then revise your plan and see how well that works. There's not really a simple automated way to do that hire fire decision within the type of mathematical tools that we're going to use in this class today. So I won't spend a lot of time talking about hire fire other than to just tell you it exists and to explain to you that the solution for a hire fire scheduling problem is predominantly just raw, hard labor. You just have to work it and manually consider all the alternatives and calculate what their outcome would be. But then what we are going to spend most of our time with is looking at how we can manipulate regular time, overtime, and inventory and contracting using the power of linear programming. We're going to bring back this topic of linear programming that we had a few weeks ago, and in particular, in this lecture, we're going to apply the transportation model. Which we covered briefly a few weeks ago in our video lecture series, in our off lecture series lessons. And the transportation model, even though you learned about it strictly in terms of literally transportation, literally shipping goods between warehouses, I will show you today how this transportation model actually is also a very close fit to this question of production scheduling, to this question of sourcing and aggregate planning model. And I'll show you how that works here in a minute. But using that transportation model, we can investigate a variety of alternatives. We can investigate mixing and matching these different sources. We can also investigate the possibility that we would do what is called a level plan. And a level plan is when we set one production level that's constant, using our regular employees, using our regular production environment. We set that as constant, and then we use inventory to balance out these highs and lows. So when demand is high and higher than our regular plan, we would we would withdraw product from inventory to fill that demand. And then when demand is lower and we don't need all this, we would then fill up inventory. We would put product into inventory and keep all of our employees working consistently through that period of time. So each one of these periods that's above or below our production level becomes either a refill or a withdrawal of inventory. And by using inventory, we can buffer customer demand and keep our manufacturing facility and our employees consistently employed and employed on a regular basis. But there's a cost to that, as we learned last week in inventory planning and inventory management. We learned there's a cost to the use of inventory. So one of the things we can do in this transportation model is we can, in fact, account for that cost. We can, in fact, include that cost in our transportation model so that the solution from our transportation model can balance out the pros and cons of inventory versus contracting versus overtime. And we will also then consider possibly not fulfilling the customer's order, failing to fill the customer's order. And we will specifically look at that in terms of a back order. That is a delayed shipment to the customer. So we can put price tags in all of these different choices, and we can put them all together in the transportation model and then actually get an optimal solution at an aggregate level. Again, this is at an aggregate level. All of this assumes that all of these options are available all the time and that there are no other constraints limiting us. And in the next week after this, in chapter 14, we will discover that sometimes there are indeed further constraints that we have to worry about. There are constraints about not having the raw materials we need, not having the correct subcomponents available to build what we need to build, and a whole lot of other things that don't show up until we start looking at this from the weekly level, at the weekly planning level. But at an aggregate level, we kind of just relax all that and just try to get a rough cut initial plan for how we're going to run our enterprise. In the real world, they would probably do an aggregate plan, share that plan with people further down the chain in management, have a meeting, discuss whether it's feasible or not, and then go back and revise that aggregate plan to respond to specific concerns that certain parts of it were infeasible. That's probably how it would be done in most firms today. So, having seen that, let's talk about how this looks mathematically, how we're going to look at this mathematically. If you take a moment to look at the handout that you have, the data slides here, we have a sample problem on these data slides. And let's take a look at what the planning problem we have here. We have a data slide where we are given some projected, expected forecast, perhaps even committed demand over a period of months. We have 6 months, January, February, March, April, May, June. We have some expected demand. And we have various ways of supplying this demand. We have a cost table on the other slide that is giving us the cost of holding inventory, the cost of purchasing product from an outside subcontractor, and the cost of producing it in-house, and the cost of producing things overtime. There are also some data items on that table for hire and fire. And as I mentioned earlier, I'm not going to do a hire-fire solution, so we don't need to worry about those particular pieces of information for this problem right now. We will not do that in this presentation. Then again, on the prior slide, the example data for the production demand, consumer demand, we also have some information about how many production days there are in the plant. What that means is that is how many days of useful work there is after holidays and weekends have been subtracted from the month, and we will take that into account in developing our model. And then there's some statistical information down at the bottom giving us some average information about this production environment. Now, using this information, we can start to discuss this problem, and the way to visualize this problem, is as a transportation model. And in fact, we will make a graph, a network graph of this planning problem, and let me start to demonstrate for you how this might look. So over here on the right, let's put demand, and let's represent demand by graphical nodes. We're actually going to draw like a graph, like a mathematical graph. We're going to draw nodes for the different time periods of demand. So there's January demand, and there's February demand, and I'm not going to do all of the data on the board. There's not enough room, so I will just do the first few months, and you can just visualize the remaining months continuing on down the bottom of the board here. But I usually just draw the first 3 months because that's all the room I have on the board to do this and keep it legible anyway. So here are our 3 months of demand, our customer demand, and I can maybe mark on there also how much that demand is. So I have a demand for 900 in January, and I have a demand for 700 in February, and I have a demand for 800 in March. And again, just visualize, I would keep going and put the remaining months down below here if I had room on the board to do this. So there's my demand. And over here on the left, let's put in on this graph our supply. Let's put in this, our supply. And again, I'm going to do this month by month. So first of all, we have, let's put in here what we have is called our regular production supply, our regular production. This is the production that occurs from our employees working their normal, regular workday. Their normal Monday through Friday workday, 8 hours a day, 40-hour work week under the North American Western assumptions. So we have a regular supply, and each month there is so much they can do in each of those regular months. Now, I'm not going to put specific numerical values on here yet because we haven't calculated those yet. Those are contingent on how many employees we decide we're going to employ full-time, and I haven't made that decision yet, so I'm going to leave those actual numbers blank on the picture here. We'll figure that out later when we're doing the spreadsheet. But, so here's our regular production, and we can visualize this as a graph. We can visualize this as a flow similar to our transportation model, and what we have is a flow. We can draw a picture, draw a flow here. And we can draw arrows connecting all the possible sources to all the possible destinations. Like that. And then repeat that for all the other months. So the February month. Like that. And if I had continued this graph down to all the other months, there would be more lines connecting those months too. I would keep on going. So if you remember the lecture and the presentation from a few weeks ago about the transportation model in linear programming, I hope you see that very quickly this is starting to look like a transportation model. This is a transportation model. We have constraints on these nodes. I haven't written the numbers in yet, but let me just put placeholders. Just pretend there's a number here. So there are numbers in each of these nodes designating how much can I produce that month under regular production. And those then represent the numerical values for constraints, for flow constraints of those nodes, just like our transportation model from a couple of weeks ago. And then I have the same thing. I have these numbers over here. These represent demand constraints, and these represent the numerical values of those constraints for each one of those nodes. And the arrows that I've drawn here, these are flows. They represent flows of product from supply to demand. And each one of these arrows, like our transportation model a few weeks ago, is a decision variable. Each one of those is a decision variable. And so we have 1, 2, 3, 4, 5, and on and on and on. Now you can imagine this gets a lot to look at. There's going to be a lot of these, and it's a lot to visualize and to see. And I just want to bring it to your attention that very often in your assignments or in your problems that you're going to do as homework or whatnot, they will use a slightly different notation to make it easier to follow. So for example, they might use a notation where there are 2 subscripts on the variables. So instead of calling this x1, maybe we would call this x January, comma, January, like that. And maybe in front of that, maybe the letter R for regular production. And then, et cetera, et cetera. And then you might see down here, X, R, January, comma, February. And so just, there's other ways to label these things than just 1, 2, 3, 4, especially when it's really complicated. There's a lot of information to portray. So just be aware that some of the problems you see, you may be presented where they've given a slightly more detailed label on the X variable to keep track of it all. So here we have 9 decision variables so far. And each one of these arcs implies a certain operation of material here. Previously in the transportation model, we were literally thinking in terms of physically moving things from one place to another. Here, in this aggregate planning model, we are not so much moving things physically in geography, but we are moving things in time. We are moving things in time and visualizing the flow of goods in terms of how we're going to move those, how we're going to deliver that item to the customer. So for example, this first decision variable up here, this arc right here, this is production today in the month of January, so to speak, from regular production, being delivered to the customer in January, in the same month. And so it's a very simple flow. There's nothing exciting going on there. But this flow right here, this next arc down, this next flow, that is production by the customer in January, by the producer in January in regular time, but it's being delivered to the customer in February. And if I'm making it in January and delivering it in February, where does it go in between? Where does it go in between?
Retailer?
Sorry?
Like a retailer?
No? Yeah?
Like a warehouse for storage?
It does go to a warehouse for storage. And it may not have to, quote, go anywhere if that warehouse is located on my facility. But it could, in a modern supply chain with all of its complexities, it obviously could be a little bit more complicated than that, and you're right. It could go to some intermediate warehouse, or there could be all kinds of, stopping off points for the material, and we might consciously start manipulating all those stop-off points in our supply chain. But at a very basic level, we're just saying it goes into inventory somewhere. Whether it's here or there or somewhere, but it's not at the customer yet. We're holding on to it. It's ours, it's in inventory, and whether it's on our factory site or whether it's in some other warehouse that we control, it is an inventory. So we have production, and then this arc representing inventory and then delivery to the customer. And likewise here, this next arc down, same thing, only how much time in inventory? 2 months, exactly. So no inventory, 1 month in inventory, 2 months in inventory. And as long as our costs and our expenses are linear, as long as we can put a fixed price on storage per month for those items, this can all be a linear program. Because we can put prices on these arcs that are nice and clean and concise, that are simply multiples of the fixed linear costs of those things. So for example, this arc up here has some dollar cost per unit. And that dollar cost up there is strictly just the cost of production. But this arc down here is going to be the cost of production plus the cost of 1 month of storage, 1 month of holding cost from our inventory concepts. And then this one down here is going to be the production cost plus 2 times our holding cost, et cetera, et cetera, et cetera. So we can assign fixed prices to each one of these arcs per unit. And that is essentially our multiplier, our cost multiplier for our objective function in the linear program. Now this arc down here, this fourth arc, going from February to January, what is that? What is happening there? That is a back order. That is a back order. What's happening there is we are making it in February and we are shipping it to the customer's original demand in January. Now we're not using a time machine, this ain't Doctor Who, we're not shipping it back to the customer in January, but that customer did ask for it in January and we failed to deliver. And then in February, we are finally making it and fulfilling that demand from January that we failed to ship. And that has a dollar cost too, and if we can assign a fixed dollar cost per time period, per unit that we are late, we call that a back order cost. If we can make that a fixed linear cost again, then once again this arc has a nice simple cost that we put right on it. The cost of production plus the back order cost. And then likewise down here at this seventh arc, it's a back order again, and now we have 2 months of back order cost. So we have that price on there, the cost of production times 2 times the back order cost. So having explained these principles, we now have a bunch of decision variables that express the quantity. Each one of these is the quantity of goods that I'm going to put on this decision path. I'm going to make sure that we have constraints that the total of those goods match up and agree with the customer demand, usually an equality. Usually this is going to be an equality constraint over here. And then over here, for the regular production, I'm usually going to say this is also an equality, because I'm going to usually say that regular production must continue at full load all the time. But then I can duplicate all of this for every other possible source in my production plan. So I can duplicate all of these nodes and make a whole other set of arrows coming out of those nodes for the overtime. For the overtime. And I can have nodes for overtime and arrows coming out of those going to the demand, and they are all decisions, more decisions. And that constraint on the overtime very often can be a less than or equal to, because I'm not required to do overtime. It's optional. So the constraints on overtime can be less than or equal to, less than or equal to. And then I can do the same thing with contracting. And I have the same kind of flows for contracting. Now, as you can imagine, this very quickly blows up to be a very large problem with a lot of decision variables. But if we stick to the format, to the structure of the transportation model that I introduced to you a few weeks ago on the Excel spreadsheet, this is still actually really not too hard. and not even very time consuming to set up in the spreadsheet. So I will demonstrate that for you tonight. But it's really not, it looks intimidating, but it won't actually be that hard. So supply, regular time, overtime, contracting, demand, all put together as a transportation network and a transportation model. Only one thing left that I want to comment on this picture before I erase it. We will sometimes also have problem situations where the problem statement says there is a certain amount of inventory available to you at the very start of the problem, or there is a certain amount of inventory we would like you to finish the problem with. And both of those can be represented very simply by just adding a little bit more to this picture. So for starting inventory, there is typically one value of starting inventory, and it's not over each month, it's just once. It's just once at the beginning of the problem. And so we could have a node over here called start inventory, and it has some value. And there would just be one of these, just one. And it would have arrows, and I'm going to make a big mess, but it would have arrows connecting to all the different demand places that I've drawn on there already. And I can't get it all in there, but imagine this start inventory source connected by arrows to all of those demands over there. And hypothetically, although it doesn't usually work out this way in most problems, hypothetically, that starting inventory could be routed to any of the future months of demand, although it's usually not a likely thing that starting inventory would end up being held for months and months and months and go way down to the end of the decision. That's really, really unlikely. But in order to keep the model complete and logical, we do include that as a possible option. And likewise, way over here at the other side, if there's a request that there be a specific end inventory, we can put in a node specifically just for end inventory. And we want to connect all the sources to that end inventory, and each so that we have some decision in the model that decides how much should end up in the end inventory as well. So, having done all that, any questions? I'm going to erase this and we'll start to build a model. Any questions about this before I launch into building the model?